Okay, so our brute force approach has failed. What we've been looking at so far, remember we're trying to understand how we turn gas into stars, quasars, whatever it might be. But all our direct imaging approaches have been looking at the things that come at the end, the stars and the quasars, the things that shine. It would be lovely if we could actually look at the gas out of which they formed. And there's a lot more of it, so it might be an easier thing to see. At the moment, we're in the situation of only seeing the end products and not what came first. It's a bit like trying to understand the evolution of humanity, having never seen a pregnant woman but only babies. It would be lovely if we could actually see the gas out of which everything formed, this neutral hydrogen.
So hydrogen itself is going to be problematic because we see that neutral hydrogen has the electron down in the ground state, and if you're going to emit, you need to fall states. Going up states doesn't really do much. So we can, we're going to have to resort to a little trick of quantum mechanics that is provided for the hydrogen atom, which is that the proton and electron within quantum mechanics have a spin. Now, it's analogous to a top spinning, and it turns out that the hydrogen atom has a different energy if those spins are in opposite directions. And it turns out it actually has a lower energy, and so you can have an energy transition when that flip occurs, and a photon comes out.
It's a bit like having two bar magnets. If you have them with North Pole to North Pole or North Pole to South Pole, you'll feel a different amount of force between them, a different energy between these two things. So when these things are spinning the same way or opposite way, there's a little tiny energy difference between them.
And that energy difference is turns out to be has equivalent to a wavelength of 21 centimeters, or about 1.4 gigahertz in terms of frequency. Now 1.4 gigahertz has a problem because we want to look back to a redshift of, let's say, 7 or 8, and that corresponds, when you redshift 1.4 gigahertz, to about 100 megahertz, which is where I listen to my music on the radio.
Yes, all the energy transfer we're talking about so far have been ultraviolet, visible, infrared. But this, because the energy gap is so small, that means the wavelength is incredibly long, which means we're talking radio waves here. If it wasn't redshifted, if it was still at 21 centimeters, we can study that because it turns out there's a band of the radio spectrum 21 centimeters that's preserved for radio astronomers. But this has now been redshifted to FM radio, which means your radio telescope, we're trying to look for the signals from hydrogen at the edge of the universe, you're going to be picking up pop music from nearby, a billion times stronger.
So one of the great things about living in Australia is there's a lot of Australia that has very, very little in it, including the Western Australian desert. And here in a place that we call Murchison, the desert has no people and no FM radio stations. And we, with partners in the United States in the form of MIT and Harvard, and also the country of India, have built a new type of radio telescope called the Murchison Wide Field Array that is literally able to tune in this distant radiation without interference from FM radio stations.
So it sounds awesome. So what you're trying to find out here is if the gas was originally neutral and then became ionized, the neutral gas will emit this 21 centimeter radiation. The ionized gas won't because the electron's not there to be flipped anymore. So you should see a signal from earlier but not later. Well, do you?
So unfortunately, the hydrogen signal is very, very weak. And so while this is a nice big radio telescope, it's not clear it's going to be big enough. So we've just started observing, and we'll know in a couple years, after we stare at the same piece of sky for a couple years, whether or not we can see things, but we may have to wait for an even bigger telescope. Now, I'm impatient, Paul, so maybe there is another way that we can get at what essentially the first stars looked like, and that is to use the principle of archaeology.
Yes, I mean, after all, when we're looking at what happened in the distant past on Earth, we don't have the benefit of being able to use a slow light travel time to go back and look at how the pyramids are built or something. We have to just look at the remains left over, the lunch wrappers or the bits of stone left over. Couldn't we do the same? I mean, bear in mind, these first stars would have been right here, as well as with the distant edges of the universe. Maybe some of them are still around.
Right, so the only problem is there's a lot of stars. This is a picture taken from the middle of the Milky Way, and there's literally 100 million stars right in the middle of the Milky Way. And we expect that maybe some of them will be the first stars, the stars formed right after the Big Bang.
But how do we tell such a star?
Well, there is that one clue that we know the first stars should have nothing other than hydrogen and helium in them. And it turns out, as we'll discuss here in just a second, and I'll show you, that how a star's, what makes up a star affects its spectrum enough that we can actually identify these things just by looking at them in the right colors of the ultraviolet.
So how can we measure how much stuff a star like the Sun has in it? Well, it turns out we can use its spectrum. And so here we plot the ultraviolet region of a star like the Sun, and indeed we plot the Sun itself here at the top. And so what you can see here is that the spectrum is made up, instead of a straight line, has lots of little divots, and each one of these little divots is the absorption line associated with an atomic transition of an element, for example, like iron. But there's more than just iron here. For example, these great big V's here are actually due to calcium. And every other element you can think of has a little divot somewhere in the spectrum of the Sun that we can identify. Now, it turns out the more calcium there is in the Sun, the stronger that line is. Or the less there is, the weaker it is. And so we've plotted here the amount of stuff the Sun has, which is about 2% of the entire Sun is stuff other than hydrogen and helium. And then we can drop the abundance by a factor of 10. So this is, instead of 0.02, it's going to be 0.002 fraction. And we go down by factors of 10 at each level, all the way down to this one, where this star has 1/100th millionth, or 10 to the 8 times less metals than the Sun. So each one of these elements becomes weaker and weaker, and when you get to a star that has almost nothing in it, the only thing you can really see in it are those two calcium lines and really nothing else. So if we are to find a star that had nothing, a nice pure spectrum like this one, we would know that it occurred very early in the universe when nothing else had been made by stars.
Okay, so Brian, you've shown that if the first stars were both very massive and very small ones, the small ones should still be around because they live longer than the current age of the universe, and they will have no sign of heavy elements on the surface. So we won't see any absorption lines due to anything other than hydrogen and helium. Well, that sounds like a testable hypothesis. Can we actually find these things?
So it turns out you can, because all of those essentially spectral lines of, for example, elements like iron, change the color of the star, even if there's just a few small amounts of stuff in it. So if you have a chemically pure star, it's going to have a different color. And so imagine taking a picture of all of the billions of stars in the sky and finding the few that have that little bit of extra ultraviolet light coming out because they don't have those spectral signatures of iron in them. And so that's a project we're doing here at the Australian National University. It's a project called SKYMAPPER, and it's a little telescope that can look at 5.7 square degrees at a time. It has a huge array of detectors, a 268 million pixel camera that can go through and look at each star.
And has special filters carefully designed to pick out that slight difference in colour. It's not something you can see by the human eye because it's in the ultraviolet, but there's a slight difference in a particular wavelength that allows you to pick out the stars that really are lacking these heavy elements.
So we've just started, but we've already found a star that has almost nothing in it. And let me show it to you. So here are some of the previous most metal deficient stars known to humanity. So for a long time, this was the record. This is a star that has about 10,000 times less iron. You can see the iron, and that depth of that line tells you how much iron there is in there. 10,000 times less than the Sun. And this is the current record holder, and this is about 200,000 times less iron than the Sun. And you can see that little divot. And here's the new
it's
star.
smaller here than it was there, which is telling you there's less iron.
And then here is the new star that we have just found. And you can see that at the iron there is literally nothing. In every place we see an iron signature in the star, there doesn't appear to be any iron. And the limit is there's less than 10 million times the amount of stuff. So there's 10 million times less stuff in the star than in the sun.
But hold on a minute. I mean, sure, it's got no iron, but it has got other elements. I mean, it's got carbon here and a few other elements show
Yeah,
up
and
in
that's
that.
calcium. So you're right, it does have stuff in it. It has even less than these. So it has stuff in it, but no iron.
So it's not really one of the first stars, is it?
So it's not one of the first stars, but it is a second star. It appears to be formed out of the debris of a single star, but it was kind of a funny explosion. These big stars, for example, a 10 to 70 times larger than our sun star that exploded, but exploded in a funny way where it made a huge black hole, so it didn't eject any iron at all. It only ejected a little bit of calcium and carbon and probably oxygen and nitrogen, and that's about it. So a very funny first star.
But this is really a bit worrying. I mean, it's a very weird, very interesting star, but where are the first stars? I mean, this is a second star. Where's the first ones?
Well, I don't know, because we haven't looked at all of the sky, but lots of people have been looking, and no one has really found one yet. So we're going to keep looking, but it may well be that there just simply aren't any first stars left for some reason. This is one of the big mysteries about the first stars.